Mars looks like the obvious choice. It has water ice, a day almost as long as Earth's, seasons, a solid surface beneath your feet. Titan has almost none of those advantages. It's farther away, bitterly cold, and sunlight there is only a fraction of what reaches Mars. By almost every obvious measure, choosing Titan over Mars sounds ridiculous. And yet, if you actually had to survive on one of them, that choice becomes much harder than it should be. Because Mars has problems that better rockets and stronger habitats don't simply make disappear. And Titan, against almost every expectation, solves some of them before we even arrive. We've spent decades imagining the first human cities on Mars. But what if we've been looking at the wrong world? What if one of the best places for humans to build a civilization isn't a planet at all, but a moon orbiting Saturn? To understand why, we have to compare what would actually happen if humans tried to live on both. The first thing you notice about Mars is the number, roughly 54 million kilometers, at its closest approach. A journey of 6 to 9 months puts Mars within the range of missions we can realistically imagine planning. And for decades, that has been reason enough to treat it as the only serious destination. Mars also has real advantages. A Martian day lasts 24 hours and 37 minutes, close enough to Earth's that your body clock adjusts without crisis. The poles hold confirmed water ice. There is evidence of transient liquid brines beneath the surface under certain conditions. The geology is varied and well mapped from decades of robotic exploration. On paper, it reads like a starting point. But the moment you try to actually inhabit the place, the list stops compounding and the constraints begin stacking. The atmosphere is 95% carbon dioxide, but at roughly 170 times less pressure than Earth's, it does almost nothing useful. It doesn't warm the surface meaningfully. It doesn't block radiation. You would need a full pressure suit to step outside, and even then, you'd be standing beneath an atmospheric column so thin it provides almost none of the protection a human body requires just to function normally day to day. Mars no longer has a global magnetic field. It collapsed billions of years ago. Without one, the solar wind has been steadily stripping the atmosphere and bombarding the surface with high-energy particles ever since. Measured radiation at the Martian surface runs approximately 0.67 millisieverts per day under moderate solar conditions, compared to roughly 0.01 on Earth. That gap doesn't close with better suits or thicker walls. It's the environment itself, accumulating across every single day a person spends there. So you build underground. Reasonable. But now you need material to construct with, machinery to excavate it, and energy to run both. And for an early Mars colony, all of it would most likely have to ship from Earth for years, possibly decades, before local manufacturing could realistically begin to take over. Mars receives only about 43% of the sunlight Earth does. The same solar array produces far less power. Then the dust storms arrive. A global storm can last months. One eventually cut the Opportunity rover's solar power so severely that contact was lost permanently. Switch to nuclear as the primary energy source. That's a legitimate path, but it adds reactor design, launch risk, regulatory complexity, and an entirely new failure mode to a colony that hasn't yet finished its first structure. Every solution generates the next constraint. That's not an engineering list you eventually clear. That's the shape of the environment working against you at every layer simultaneously. Then you look at what's sitting 1.4 billion kilometers from the Sun, and the logic starts moving somewhere unexpected. Saturn's largest moon Titan was discovered in 1655. For most of the time since, it appeared as a featureless orange dot, completely opaque to every instrument pointed at it. Voyager confirmed it had an atmosphere. It took Cassini, arriving at Saturn in 2004, to reveal what was actually underneath. Lakes, hundreds of them, not dried basins, not geological fossils of ancient water. Active, liquid lakes, some larger than the Caspian Sea, spread across the northern polar region, observed directly over 13 years of orbital passes. They're not filled with water. At Titan's surface, temperature of around -179 degrees Celsius, water is as solid as granite. What fills the lakes is liquid methane and ethane, hydrocarbons cycling through evaporation, cloud formation, and rainfall exactly the way water does on Earth. Methane droplets fall from orange clouds, carve channels into the surface, and eventually drain back toward the lakes. Cassini watched this happen. The cycle is ongoing. Titan isn't a frozen relic. It's a world with a functioning, active surface environment running on entirely different chemistry than ours. But the single number that rewrites the entire comparison is simpler than any of that. Titan's atmospheric surface pressure is approximately 1.5 bars. Not thin, not barely there. Thicker than the air you're breathing right now. That one measurement collapses the central problem that makes Mars so dangerous to inhabit. You don't need a pressure suit on Titan. The atmosphere is unbreathable. Nitrogen and methane, with no free oxygen, so you need a breathing apparatus. But the pressure itself won't harm you. A well-insulated suit with an oxygen supply would let you walk on Titan's surface without the environment mechanically destroying your physiology in the process. That same dense atmospheric column provides substantial radiation shielding. A thick nitrogen atmosphere absorbs and scatters high-energy particles far more effectively than Mars's near-absent atmosphere ever could. On Mars, radiation is a problem you have to engineer around indefinitely. On Titan, a large part of that shielding is already there in the atmosphere, doing the protective work that Mars's sky simply cannot. For a moment, Titan looks like it has won the comparison. Then you notice the gravity. Titan's surface gravity is only about 1.4 meters per second squared, roughly 14% of Earth's. For comparison, Mars reaches 3.7 meters per second squared, about 38%. Both fall far below what the human body evolved under. But Titan's is in a different category entirely. We don't fully understand what long-term exposure to very low gravity does to a human being. The research we have comes from astronauts aboard the International Space Station, where months in microgravity cause bone density loss, muscle atrophy, cardiovascular changes, and fluid shifts that don't fully reverse after returning to Earth. And those are people who go home. On Titan, there is no going home. Children born there would develop under conditions no human body has ever experienced across a full lifetime. What that produces, biologically, across generations, is a question nobody has been in a position to study. So Titan's atmosphere solves the radiation problem Mars cannot solve, and then quietly introduces a biological unknown of its own that may be just as serious. Neither world is obviously safe, and that changes the question entirely. At one point, 4 billion kilometers from the Sun, Titan receives roughly 1% of the solar intensity that reaches Earth. Solar panels at that distance are not a viable primary power source. That's a hard physical constraint, and it doesn't soften. This is where most arguments for Titan stall, and it's a legitimate problem. one that shouldn't be minimized. But Titan's surface is saturated in hydrocarbons, methane, ethane, acetylene, complex organic molecules raining continuously from the atmosphere, pooling into lakes, coating dune fields. These are energy-dense chemical feedstocks, not materials that need to be synthesized from scratch or imported across interplanetary distances. They're sitting at the surface in liquid and solid form. To release energy from them through combustion, you need oxygen. Titan's atmosphere contains none in free form. But Titan's crust holds substantial quantities of water ice, and water ice given sufficient energy input can be split into hydrogen and oxygen through electrolysis. The oxygen feeds combustion. The hydrogen is usable in fuel cells. The raw materials for a chemical energy system are locally present in an unusually convenient form: hydrocarbons already accumulated on the surface, alongside abundant water ice. That combination doesn't exist on Mars in anything like the same configuration. But here is where the argument has to stay honest. Methane is not an energy source in the same sense as a nuclear reactor or incoming sunlight. It is chemical energy storage. You have to put energy into producing the oxygen and processing the materials before you can extract anything useful from the combustion cycle. Nuclear power would almost certainly remain the primary energy source for any Titan colony for the foreseeable future. The local hydrocarbons would become valuable chemical feedstocks and energy storage materials once sufficient infrastructure exists to use them. That's a meaningful advantage over Mars, where the equivalent local resource base is far thinner. But it's not a solved problem. It's a direction that makes the energy challenge more tractable than it first appears, which is different from making it easy. The question of which world is actually viable keeps shifting the more carefully you examine it. And the final layer isn't about atmosphere or energy or radiation. It's about what a colony fundamentally needs to survive, not across years, but across centuries. A crewed mission to Titan using foreseeable technology would take somewhere between 5 and 7 years in transit. That number ends most conversations about Titan immediately. It's a serious constraint, and treating it otherwise would be dishonest. But whether distance is ultimately fatal depends entirely on what the colony still needs from Earth once it arrives. Early Mars colonies are likely to remain highly dependent on Earth for a significant period. Energy infrastructure, construction materials, manufacturing equipment, food production systems, all of it would need regular delivery because Mars's accessible local resource base, while real, is difficult to process at the scale a human settlement demands. The long-term goal is absolutely to develop local production. But in the critical early decades, that dependency creates a fragility that distance turns into a genuine existential risk. A supply chain across interplanetary distances is only as strong as its least reliable link. Titan's resource base, atmospheric nitrogen, surface hydrocarbons, subsurface water ice, complex organic chemistry already present in abundance, potentially offers more of the raw materials required for long-term self-sufficiency than Mars does. Whether that potential can be fully realized is genuinely unknown. We haven't sent humans there. We haven't built anything there. But the ingredients exist in a configuration Mars doesn't match. And that matters when you're thinking across decades rather than individual mission windows. Then there's the radiation biology, the part that doesn't appear in most comparisons. Long-term human exposure to Mars's radiation levels remains one of the most poorly understood risks in spaceflight planning. Colonists would be accumulating biological damage continuously across years and decades, damage whose full consequences remain unobserved because no human being has ever spent years on Mars. The first generation of Mars colonists would be running an uncontrolled experiment on themselves, with no exit option and no way to know the outcome until it was already too late to change course. On Titan, the thick atmosphere reduces that particular risk substantially, but Titan's gravity introduces its own uncontrolled experiment, one that runs across generations, with consequences we have no data to predict. So here is where the comparison actually lands. Mars is easier to reach. Titan may be easier to sustain. Mars offers shorter travel time, stronger gravity, and decades of robotic reconnaissance. But early colonies would be heavily Earth-dependent, and the radiation environment accumulates biological damage in ways we haven't solved. Titan offers an atmosphere that handles radiation naturally, a richer local resource base, and surface pressure a human body can tolerate without a suit compensating for near-vacuum conditions. But its gravity is so low that we genuinely don't know what it does to the human body across a lifetime, and the distance makes early dependence on Earth an enormous logistical problem. Neither world is obviously the right answer. That is the honest conclusion after decades of serious Mars exploration and 13 years of studying Titan up close. And one of those worlds has been studied extensively as a destination. The other has barely been studied as a place for humans to live. We chose Mars because it was close enough to feel possible. Titan looked like the wrong answer entirely. Distant, frozen, low gravity, wrapped in orange chemical haze. But the radiation problem at the center of every Mars colonization plan remains unsolved, and Titan's atmosphere, its methane lakes, its organic chemistry, its surface pressure, those aren't minor details. They're the properties that determine whether a place can sustain human life across generations, not just receive a visit. Mars is easier to reach. Titan may be easier to sustain. That distinction doesn't resolve neatly, and it probably shouldn't. The gravity question alone could disqualify Titan entirely, and we won't know the answer until someone actually tries. But we've spent decades failing to solve what Mars does to a human body over a lifetime spent there. Maybe the more useful question is one we've barely started asking. Titan has been there since 1655. We just haven't been looking at it properly.